So in today's lecture, we are going to discuss the motion of the charged particle in a magnetic field. Right, you may heading is motion of charged particle in magnetic field. Right, magnetic field. So if you consider there is a magnetic field, right? Suppose this is the magnetic field over here, right? The magnetic induction is B, and a charged particle, suppose this is the plus Q, or any charged particle Q is moving with some velocity V at angle theta, right? The charged particle suppose is moving with velocity V and making angle theta with, then, right, if charged particle, if Q is moving with velocity v, with velocity v in magnetic field, B, right, then magnetic force act upon this, magnetic force acts upon it, right, and it is given by, right, the magnetic force on a moving charged particle is given by Q. Q is the charge V cross B, right? It is V cross B. This is the magnetic force on the moving charged particle. Is it clear or not? So if you suppose this is the velocity V and this is the magnetic field B angle theta, if you write down its magnitude QVB sin theta, all right, where what is theta? Angle between the velocity vector and magnetic field vector, all right. In this case 1, you can choose that if the magnetic field is in this direction and the charged particle is either moving in the same direction as that of B, right, or it may be moving, right, opposite to the magnetic field direction. So in this case V and B both are in same direction, so angle is theta is equal to 0 degree, or when it is moving opposite to this, then theta is what, say 180 degree. So in both cases the magnetic force is nothing but QVB sin theta, right, and sin 0 value and sin 180 value is equal to what, say 0. Sin 0 and sin 180 value is what, say 0, right. So magnetic force acting upon this will be 0. Is it clear or not? That is, no magnetic force acts upon this charged particle, right, charged particle, if it is moving along the magnetic field or opposite to the, just opposite to the magnetic field. So particle moves undeviated. Is it clear or not? Particle moves undeviated. The magnetic force acting on this type of the particle, which is making angle theta is equal to 0 and 180 degree is equal to 0. So no magnetic force act upon this. But you may consider the case 2, the very important thing. If for the maximum magnetic force, tell me what should be the value of, it depends upon the theta, right? For the maximum magnetic force, what should be the value of the theta you tell? Say 90 degree, right, because sin theta is maximum for theta is equal to 90 degree, right. So therefore the magnetic force maximum will be equal to what, QVB sin 90, and its value is what, QVB, because sin 90 is 1. This is the magnetic force, maximum magnetic force act upon the moving charged particle, right? You understand? Listen, one more thing. If you consider, if the charged particle is at rest, that is, if charge particle is at rest, what does it mean? Suppose this is the magnetic field, right, and this is the charged particle, and it is at rest, it is not moving. So if it is at rest, no, it is not moving, what will be the magnetic force? Say 0. It means if charge particle is at rest, no magnetic force applied upon it. No magnetic force applied on it, right? Copy this. So now let's see the motion of charge particle. Motion of charge particle in uniform transverse magnetic field. Transverse magnetic field means the magnetic field is perpendicular to the velocity of the charge particle. This is the very special case, and number of questions are formed, right, on this type of case. Suppose the magnetic field is into the board like this. All right, the magnetic field is into the board. Now if you consider this, that suppose the plus q charge is there, right, it start moving with velocity v, right? Listen one thing, if you consider the magnetic force is equal to qv cross b, right? The magnetic force is a vector quantity and its direction you may write here in the left side, right, somewhere. Direction, what is the direction of magnetic force? Direction of magnetic force is along v cross b, right, along v cross b, or given by Fleming left hand rule, right, or given by Fleming left hand rule. And what is that? Listen one thing, if this is the, suppose this is the plane, right, this is the plane, are you getting or not? This is the plane. If this is the charge particle q, and this is the velocity of the vector and this is the b vector, and the angle between them is what? Theta. So what is the direction of v cross b? The v cross b is along this direction. This is the direction of v cross b. If this is the a vector, this is the b vector, right? So what is the, suppose this is the plane, right, you consider this is the plane, all right, like this, and if this is the value of a, this is the value of b, both vectors are supposed to be in same plane and the angle between them is supposed to be theta, right, it is a vector. So then this is the direction of a cross b, if you understand, the a cross b, and what is this direction? You tell, minus a cross b. Are you getting or not? So in the same way, the magnetic force is given by in the direction of q v cross b. So if it is v and this is b, this is the direction of the magnetic force. If this charge is plus q, are you getting or not? On the plus q charge, the force is in this direction. Are you getting or not? Suppose if this is the another charge, right, suppose this is the another charge minus q, and it is moving with velocity v, and this is the magnetic field b, and angle is theta, all right. So the magnetic force is what? Say minus q v cross b. This is the magnetic force. Is it clear or not? You tell. This is v cross b direction, this is v cross b direction, but the force is opposite to v cross b. For example, if this is a cross b, right, a cross b, and this direction is what? A cross b, or you may write minus b cross a, right. So this is b cross a or minus a cross b. So if this is the plus q charge, the force is along v cross b, but if it is minus charge, the force is opposite to the b cross b. This is the direction b cross b, but the force is in this direction. So this is the direction of the magnetic force. It is found by the right hand rule, right, like this, right. First copy this. Before copying this, first copy this, right, how to find the direction. So this is the one way to find the direction, right. And what is the Fleming left hand rule? right? For example, this is the 3D view I have given, and the direction of the magnetic force is given by V cross B for the positive charge, for the negative charge minus QV cross B, right? If this, suppose this is the perpendicular magnetic field and this is the plus Q charge, it is moving in this way, right, with the velocity V. Fine. So what is the direction of V cross B? Take your left hand. This finger, index finger, represent the magnetic field. The magnetic field is here into the board, right? This is the magnetic field. It represents the velocity direction. Magnetic field, it represents the velocity direction, and thumb represent what? The direction of the magnetic force. So here the magnetic force act upon this. Is it clear or not, you tell? Right? Suppose this is the perpendicular magnetic field like this, and the plus Q charge, this is the plus Q charge, is going in this direction. So you have to find the magnetic force. First of all, in the perpendicular magnetic field, either the magnetic field will be into the board or out of the board, right? And the velocity will be in this plane like this. So take your left hand. The magnetic field is into the board. This is the direction of velocity. So the thumb represent the direction of the magnetic force. Is it clear or not, you tell? Right. But if you consider this is the out of the board magnetic field, all right, this is the out of the board magnetic field. Are you getting or not, you tell? And if this plus Q is moving in this way, suppose, right, this is the plus Q charge. So Fleming left hand rule, you have to take your left hand rule, not left hand, not the right hand, right? So take your left hand. This index finger represent the direction of magnetic field like this, and it represent the velocity. Are you getting or not? Yes. This is the magnetic field out of the board. This represent the velocity. The thumb represent what? Force. So on this particle, where the force will act? In this direction. Right. Force is always perpendicular to velocity. Suppose this is the velocity. So either force will be acting in this direction or perpendicular to this direction. Is it clear or not? Yes. This magnetic force, in this figure also you can say, this magnetic force is perpendicular to the magnetic field, right? Perpendicular to the magnetic field and perpendicular to the velocity. Is it clear or not, you tell? Yes. Because it is along the direction of the V cross B. So you may write here, this magnetic force is perpendicular to the velocity. Also, the magnetic force is perpendicular to the magnetic field. Are you getting or not? So here this magnetic force and velocity are always at 90 degree, right? Copy this, copy this. Right? Yes. Okay, now we can continue this. The motion of charged particle in uniform transverse magnetic field, or you can say perpendicular magnetic field, right? Perpendicular magnetic field. Is it clear or not, you tell? So suppose the magnetic field is into the board, right? Magnetic field is into the board. So, and suppose this is the plus Q charge. So if the magnetic field was not present, what will happen? If charged particle is moving, it will continue to move in a straight line or not, you tell? Yes. If magnetic field is not there, right, there will be no magnetic force acting upon this, and the charged particle will go undeviated, right? But when the magnetic field is switched on, and this charged particle, moving charged particle, come under the magnetic field, transverse magnetic field. So the magnetic force start acting upon this, and the magnetic force is given by this expression. what is the direction of the magnetic force? You tell. Take your left hand rule. Take your left hand. It is the magnetic field, it is the velocity. So what is the direction of magnetic force? Upwards. So you tell me. So if the magnetic force acting over here, then what will happen to its motion, path of the motion? You tell. It will move in a straight line or it will deviate it? Yes, it will deviate it. Now suppose the velocity become, listen one more thing, this magnetic force is always perpendicular to the velocity. Are you getting or not? So therefore it does not do any work. This magnetic force does not do any work, right, on the charged particle. Its speed does not change, right? I will explain this again also, right? So suppose its velocity is v now, right? So again, if this is the plus q charge particle, getting, magnetic field is into the board, it is the velocity or not? So what is the direction of magnetic force? Say along the perpendicular to the velocity, like this. Is it clear or not, you tell? And because of this, it will again deviate it. So when it reach at this point, so its velocity become, say, v. All right, this is the plus q charge, suppose, right, and the magnetic force act upon this in this direction. Is it clear or not, you tell? Right, how? Magnetic field, velocity and magnetic force. Are you getting? So if the magnetic force not there, it must go in a straight line, but because of this force it deviates again. So here it deviates like this, right? So it start performing circular motion in this circle. Is it clear or not? And if it is moving on a circle, so there will be some center of the circle. Suppose it is moving at this point with the speed v, so the magnetic force act towards the center. When it is moving at this point with the speed v, the magnetic force acting toward the center. So if the perpendicular magnetic field is there and the charged particle given a velocity v, so it will not move in a straight line, rather in perpendicular, in transverse magnetic field, right, is a uniform circular motion. Are you getting or not? You may write, therefore therefore charge particle perform uniform circular motion in perpendicular magnetic field, perpendicular magnetic field, and required centripetal force, because it is performing UCM, uniform circular motion. So if the charged particle is moving in a circle, so there must be some required centripetal force, and this required centripetal force is provided by the magnetic force acting upon this, because only the net force acting toward the center is Fm. Is it clear or not, you tell? Right. Charged particle perform uniform circular motion in perpendicular magnetic field and required centripetal force. Centripetal force is obtained by magnetic force acting upon this, magnetic force acting upon it. That is, the magnetic force provide the required centripetal force. And what is the centripetal force? Say mv square upon r. If r is the radius of this circular path, right, so the magnetic force is what? You tell. What is the magnetic force? Say qvb sine 90. Why? Because the angle between the velocity and the magnetic field is into the board, it is velocity. So 90-degree angle. So it is qvb. So what is the magnitude of the magnetic force? Say qvb is equal to mv square upon r. Are you getting or not? Right. So what is the radius of the path? So the speed v is cancel out. Qb is equal to what? Mv upon r. implies that the radius of the charged particle is mv upon qb. Is it clear or not? So I'm writing this side, you may write. So the radius of, therefore radius of circular path is given by r is equal to mv upon qb, right? Copy this. So the radius of the circular path and a uniform circular path of the charged particle moving in transverse magnetic field is given by mv upon qb. So mv is what? Say momentum, right? P is what? Say mb, it is called the momentum, right? So r may be written as p upon qb. Listen, one more thing, from here the radius is proportional to velocity. You must remember, radius is proportional to velocity. What does it mean? It means if you give this the charged particle, suppose the perpendicular magnetic field is into the board. If you give the small velocity, the radius of this charged particle will be small. All right. If you increase the velocity v2 from v1 to v2, what will happen? The radius of the charged particle will increase. So now the radius become r2, the more radius. Is it clear or not, you tell? Right. Initially it is the center of this circle. When you give the velocity, the center of the circle is this. So radius become more of this circle. Right. Like this. Are you getting? Now let's see the time period. Although the radius formula in terms of the momentum may be defined, may be represented in different many ways. Suppose this is the kinetic energy is equal to half mv square, right? If you multiply by m in the numerator, therefore it is multiplied in denominator. Are you getting? So it is p square upon 2m, because p is nothing but say mv, right? So kinetic energy is nothing but p square upon 2m. You know this implies that p square is equal to what? 2m into kinetic energy, and the momentum is nothing but root 2m into kinetic energy. So what is the radius? The radius formula is mv upon qb, but in place of mv or the momentum, right, it may be written as 2m into kinetic energy into q into b. Is it clear or not, you tell? Yes. Right. This is the one another formula. Now sometime the kinetic energy of the charged particle is given as it is. So to find the radius we can use this expression, right? But sometime it is given if charge particle is accelerated by, right, potential difference delta q. If charge particle q is accelerated by potential difference q, delta q, then its kinetic energy is nothing but q into delta v, right? Potential difference delta v, sorry. If charge particle q is accelerated by potential difference delta v, then its kinetic energy is given by q into delta v, because w is equal to what? Q into delta v. So this w is equal to nothing but q into delta v. So you will always remember the charge particle kinetic energy is given by q into delta v if it is accelerated by potential difference delta v. All right. So here radius formula, radius of the circular track will be given as 2 into m into q into delta v upon q into b. Is it clear or not? So listen, the q, this q is in square root and it is denominator, so it may be written as b, 1 upon b as it is, root 2q m into delta v upon q. So the radius may be given by 1 upon b is the magnetic field, and q comes under the square root m into delta v by q. So this is the radius of the circular track, right? Copy this. So if the charged particle is moving in a circular track its motion will be circular, uniform circular motion. The direction of the velocity will be changing due to this magnetic force, but speed remains constant. And the radius of this charged particle is given by either this expression or this expression you can use, right? Now, the second thing is the time period of oscillation, right? After this, you may write here, right? The second point is time period of revolution, right? Revolution. All right. How to find the time period of revolution, Newton? The total time to complete one circle is called the time period of revolution. This is the one thing. And the t is nothing but 2 pi r upon v. Total distance is what? 2 pi r. And by what speed it is completing this circle? By v. So it is 2 pi r. What is r? Say r is equal to mv upon q into v. Is it clear or not, you tell? The vv will cancel out and t is equal to what? Say 2 pi m upon qb. Fine. This is the time period to complete one circle, 2 pi m upon qb. And look, in this expression of time period, the speed is not there. This time period, right? This time period, capital T, does not depend upon the speed, right? Is it clear or not? Whether speed is more or less. If it is less, its radius will be less. If it is more, its radius will be more. But time period is 2 pi q by m. The charge is q every time, the magnetic field is b every time, and the mass does not change of the charged particle. So if we take the time period t, t1 and t1, so t1 and t2 will be equal according to this relation. What does it mean? I am explaining this side, right? You may write this side. For example, if suppose this is the perpendicular magnetic field over here, all right, and if you give some velocity to the charged particle, right, q, so what will happen? The magnetic field is into the boat, the magnetic force act upon this, so it will be the direction of the circle, it will be the position of circle somewhere, so it will move in a circular path or not, you tell. And the radius is what? mv upon qb, and time period is what? 2 pi m upon qb. Is it clear or not? Yes. Now, if the same charge particle is given the velocity v dash, and the v dash is greater than v, if v dash is greater than v, right, so the magnetic force will also be increased, and therefore it takes this path, and the radius is what? Say r dash. So what is the r dash? Say mv dash upon qb. Is it clear or not? Yes. Because v dash is greater than v, therefore r dash is greater than r. So radius of the circular track is increased, but if you consider the time is equal to 2 pi m, m is the mass, right, upon q into b. So is it same or not, you tell, right? So if you take time t to cover this, the time t to cover this circle. Are you getting or not? But radius will be different, right? So this is the expression for the time period, right? Copy this. So this is the expression for the radius, this is the expression for the time period of a charged particle moving in a circular path, right, in a uniform perpendicular magnetic field, right? Especially this is the case. Important thing, if you consider the force is always perpendicular to the velocity. Listen, since the direction of the velocity is changing, so if you write down the velocity vector, right, if it is v1 and v2, and suppose this is the v3 and this is the v4 vector, also the magnitude of the magnetic force is constant, but its direction is changing. So if this is the fm1 vector, this is fm2 vector, like this, 3 4 vector, like this. So velocity, listen one thing, velocity v1, v2, v3 and v4, they are not equal, since their directions are not equal, but their magnitude are equal. This is the first thing, right? Their magnitude that is their speed is constant. Is it clear or not? In the same way, although the magnetic force are not equal, but their magnitudes are equal. Are you getting or not? Is equal to QVB. This is the magnetic force. Since the magnetic force is perpendicular to the velocity every time, right? Every time. Are you getting? So what is the power delivered? Power delivered by the magnetic force. So therefore, power delivered by magnetic force. Magnetic force. What is the power delivered by the magnetic force? Power is nothing but Fm dot V. Is it clear or not, you tell? Yes. Fm dot V, instantaneous power. And since Fm is perpendicular to V, therefore their dot product will be equal to what? Say FMV cos 90, and the cos 90 is 0. So its dot product is 0, therefore the power delivered is 0, right? Yes. What is the power delivered by magnetic force? 0. Therefore, if no power is delivered by the magnetic force, that is the no work is done by magnetic force. So therefore, no change in kinetic energy. Since the power delivered is 0, therefore no work is done. No work is done by magnetic force. Magnetic force, right? Therefore, no change in kinetic energy. No change in kinetic energy. And if change in kinetic energy is not there, you may write, therefore, speed remains constant. Speed remains constant, right? That is the thing. Copy this. So, read this question. In this question, a charge Q is equal to minus 4 microcoulomb, rise, has an instantaneous velocity 2I minus 3J, right, plus K into 10 to the power 6 J cap, right, oh sorry, meter per second. In a uniform magnetic field B, 2I plus 5J minus 3K into 10 to the power minus 2 Tesla. Now you have to find what is the force on the charge. So what is the magnetic force formula you tell? Say Q V cross B. All right. Right. So here the charge will be put with the sign. If it is minus 4 microcoulomb, right? What is the velocity vector? 2I minus 3J plus K into 10 to the power 6 cross. This is not multiply, it is cross with the magnetic field vector. It is 2I plus 5J minus 3K minus 2. Is it clear or not, you tell? So this minus 6 will cancel out. It is minus 0.04, right? 4 into 10 cube. And this is the cross product. Whose cross product you have to do? This vector and this vector. So I, J, K. What is the component? What is the coefficient? 2 minus 3, 1. 2 minus 3, 1. The coefficient of this vector? 2, 5 minus 3. 2, 5 minus 3. Is it clear or not? Yes. Minus 0.04. This is the magnetic force. Now, we have to find this cross product by determinant method, right? So, what is the determinant method? Listen one thing. This is the I cap minus J cap and this is the plus K cap. So, the cross product will be in the form of I cap, J cap and K cap. When you are writing the coefficient of J, the minus sign is over there, as you know, right? To find the coefficient of I cap, just hide this, all right? Multiply, cross multiply, minus 3, 9, right? Put the minus sign from your side and then again cross multiply, 5. Is it clear or not? To find the coefficient of J, hide this coefficient. So what we have? We have 2 minus 3, 1 minus 3. So it is what? Minus 6 Put the minus sign from your side and 2 1 ja 2. Are you getting or not? You tell. So when you want to write down the k coefficient, hide this. So what is left? You tell. 5 2 2 minus 3 5. Multiply this. 5 2 ja 10. Put minus sign from your side and multiply, cross multiply. 2 minus 3 minus 6. Is it clear or not? You tell.
Yes.
Right. So in this way, the cross product you must understand, you must know, right, how to make the cross product. It is minus 0.04. This is 4 I cap. Minus plus 8 J cap. This is 16 K cap. Right. This is the magnetic force. The unit is Newton. Is it clear or not, Newton? Right. Copy this. So read this example. A test charge, and the charge is 1.6 into 10 to the power minus 19 coulomb, and the velocity is given as 2I minus plus 3j cap meter per second, and the magnetic field is under 2I plus 3j cap meter per second. Right? Is it clear or not, Utal? So you have to find the magnetic force. So magnetic force is QV cross B. Is it clear or not, Utal? So if you look the velocity and the magnetic field, what is the direction? Tell me. Both are in same direction. Is it clear or not, Utal? So angle between them is 0. So what will be the magnetic force? Tell me. Say 0.
Yes.
Right. V cross B, VB sine theta. If theta is 0, then the cross product is also 0. Although you can do in this way. Although the magnetic force comes to be 0 in this case, but this is the first method you can say. Right. Second method, directly you have to make the cross product. Right. Fm is equal to what? Say QV cross B. Right. The Q is Q. You may write this later. It is 2I plus 3j. Right. Cross 2I plus 3j. Right. If you make the cross product, although it is a small vector, so we may find the cross product individually. Right. For example, what is the I cross I? Please tell. It may be written as 2I cross 2I plus 3j. Right. Then multiply by 3j cross 2I plus 3j. Right. First multiply by 2I whole bracket, then multiply or cross product of 3j whole bracket. Is it clear or not, Utal? So this is 2 2 ja 4 I cross I, 2 3 ja 6 I cross j, then 3 2 ja 6 j cross I plus 3 3 ja 9 j cross j. Is it clear or not, Utal?
Yes.
What is the I cross I? 0. And j cross j? 0. I cross I is 0, j cross j is 0. And it is I cross j and this is j cross I. So according to the property of the cross product, I cross j is equal to minus j cross I. Are you getting? So it is q 6I cross j, right, plus 6. What is j cross I? J cross I may be written as minus I cross j, right? And this is I cross j, this is I cross j minus. So what is the answer? The magnetic force is 0. Although no need to do all these things, because once we know the two vector, velocity vector and magnetic field vector, are in same direction, their cross product must be 0. All right, copy this. So read this question. In this question, a charge with 10 to the minus 11 coulomb, the mass is 10 to the minus 7 kg. Right. Velocity is given as 10 to the 8 along the x-axis, I cap meter per second. Uniform magnetic field is given as 0.5 Tesla along the y direction. So the magnetic force Fm you have to find, right? I think you know the formula. What is the magnetic force? Say it is Q V cross B. All right. The Q is 10 to the minus 11. The velocity vector is 10 to the 8 I cap cross. It is 0.5 J cap. Is it clear or not? You tell. So when you simplify, it is 0.5 into 10 to the power minus 3. Fine. Into I cross J. What is the I cross J? Tell me. I cross J is equal to I cross J is equal to K cap. And what is the J cross K is equal to? No. J cross K is equal to I cap. And K cross I is equal to J cap. I J K. I cross J. J cross K. I. K cross I. J. And if reverse is there, I think you know this. So I cross J is equal to what? 0.5 into 10 to the power minus 3 K cap. Newton is the force. It may be written as 5 into 10 to the power minus 4 K cap. Newton is the force. So which option is the correct option? K cap along, K cap mean along Z direction. Along Z direction. So second option is the correct option. Copy this. So read this question. In this question, 2 mega electron proton is moving perpendicular to uniform magnetic field 2.5 Tesla. The magnetic force on that proton you have to find. The proton mean the charge is plus E is equal to 1.6 into 10 to the power minus 19 coulomb, right? And the 2 mega electron proton mean the energy of the proton is given as 2 mega electron volt, right? So 2 mega mean 2 into 10 to the power 6. 2 mega electron mean 1.6 into 10 to the power minus 19. So this is the energy in joule. So half mv square, can I write this? Right. Now we can find its speed. The mass of the electron is, the mass of the proton is 1.67 into 10 to the power, right, minus 27 into v square is equal to 3.2 into 10 to the power minus 13, right? 16 to the 3.2, right? 32. Now if you multiply v square is equal to 3.2 into 2 into 10 to the power minus 13 divided by 1.67 into 10 to the power minus 27. Listen one thing. For simplicity, the mass 1.67 may be written as approximately 1.6, right? So you may write this the 1.6. So it is 2 and 2 to the 4 into 10 to the power minus 13 plus 27. It is equal to 4 into 10 to the power, right? It is 414. So this is the v square. If you take the square root, 2 into 10 to the power 7 meter per second is the speed of the proton moving in this magnetic field. The perpendicular magnetic field is given as 2.5 Tesla. Now how to find the magnetic force, you tell? Say QVB sine 90, right? Sine 90 is 1 because the magnetic field is perpendicular to the moving charge particle. The charge, proton, the charge is 1.6 into 10 to the power 19. The speed is to be 2 into 10 to the power 7. And the magnetic field is 2.5 Tesla, right? So this is 3.2 into 2.5 into 10 to the power. This is minus 12. All right. Now 3.2 and 2.5. 5 दूनी 10, 5 से 15, 16 into 64,008. So this is 8 into 10 raised to minus 12 Newton. Right. So the magnetic force come out to be 8 into 10 to the power minus 12 Newton is the correct answer. So which option is the correct option, you tell? The first option is the correct option, right? Copy this. So read this question. In this question, an electron is moving, right? Suppose this is the wire in a direction parallel to the current. What is the current in the wire? say it is 5 ampere, right? And this is the electron, this is the minus C, is moving with the speed v, 10 raised to 6 meter per second. Are you getting or not?
Yes, sir.
Perpendicular distance is what? Say 10 centimeter, right? Magnetic force experience, you have to find the magnetic force experience by this. Listen, to find the magnetic force, suppose this is the current, infinite current carrying wire. So at this point magnetic field will be into the board, and this side magnetic field will be out of the board. So this charge is moving, that is this electron is moving at with velocity this. The magnetic field is say into the board, right? And this is the negative charge, this is the minus C charge. So first we have to find the magnetic field at this point. So B is equal to what? Say mu naught I upon 2 pi d. Is it clear or not, you tell?
Yes, sir.
And magnetic field is into the board. The velocity is in this direction. So magnetic force should be in this direction or not, you tell?
Yes.
But it is negative charge.
Opposite.
Yes. So therefore, for this electron, the magnetic force will be in this direction, but the magnitude of magnetic force will be QVB, right? QVB. Is it fine or not, you tell?
Yes, sir.
So what is the Q? I'm finding the magnitude. So I will write the charge is nothing but 1.6 into 10 to the power minus 19. The speed. What is the speed? 10 to the power 6. What is the magnetic field we have to find at this point? It is not given in the question. So mu naught value is 4 pi into 10 to the power minus 7. The current value of I is 5 ampere. 2 pi into D. D is what? Say 0.1. Are you getting?
Yes.
So it is 2. 10 into 10 to the power minus 7 upon 0.1 is equal to 10 to the power minus 5 Tesla. Right? Minus 5 Tesla. Is it clear or not, you tell?
Yes.
So it is 1.6 into 10 to the power minus 18 Newton is the correct answer. Right?
Yes.
Copy this.